Well, welcome everyone. My name is Salman Iqbal. If you're here for the F-sharp talk, this ain't it, because we're going to talk about Kubernetes and Kubernetes Scheduler. The speaker who was supposed to do, I know you're a bit disappointed, but hopefully you won't be at the end of this session. The speaker who was supposed to be here can't make it, so I just jumped in last minute to do this talk. So if there's any mistakes or anything like that, please forgive me, but hopefully we'll all have a good time. I do have another talk. Are we good to share the screen? Okay, I do have an actual talk that I was supposed to do in NDC on Friday. It's about running machine learning stuff in the cloud at scale, and how can you do it in a cloud agnostic way. And that's what I'll be talking about on Friday. So if you are into DevOps, cloud, machine learning, or want to get into machine learning, data science, that talk you'll find useful. So first of all, I'd like to say thank you all for coming. And if you're not here for the F-sharp talk, if you're here for the F-sharp talk, this is not it. But hopefully, so what we're going to talk about is Kubernetes and how Kubernetes places its workloads in the cloud. If you have to leave at any time, feel free to leave. But hopefully, we can go through it. I'm not going to take the full hour, so I think it should be good. Let me just quickly play this, and we'll start. How's everybody's conference so far? First day, good? Yeah? I see some thumbs ups and nods. It's about to get better. So I know I said, so the title of the actual talk is, how does Kubernetes play Tetris with your containers? Just as a show of hands, just for my interest, how many people in this room have run containers? Even if just like, okay. Oh, so pretty much everybody. Awesome. How about played around with Kubernetes? Yeah, cool. So we got half the room. And if you've not played around with Kubernetes, great, because we're going to talk about what Kubernetes is. We won't go into too much detail, but if you have any questions afterwards or during the talk, feel free to ask. I will answer. And I think it will be even better if you have any questions. If something doesn't make sense, please ask, and I will answer during the talk. I think we'll keep it interactive that way. So my name is Salman Iqbal. The best way to find me is on Twitter, so you can search me as Salman Iqbal. People think because I can sing, that's why my handle is Salman, but I cannot sing. I just couldn't get a handle Salman Iqbal, so I stuck with Salman Iqbal. And I work as a Kubernetes instructor with Learn K8, so it's a company that we provide Kubernetes training. And I also work as an MLOps engineer with a company called Appia, and MLOps is all about data science for DevOps. And I am part of community, so I come from Wales in UK. Anybody from Wales here? Yeah, I thought so. Just me. So we run a cloud native community in Wales with my friend, and you can find me on Twitter. I do actually have a YouTube channel, so you know what people say, like and subscribe. So if you want to learn a bit more about Kubernetes stuff, I do post Kubernetes stuff. Please forgive the cheesy thumbnails, but you got to do it for the for the titles. If you want to learn a bit more about Kubernetes, that's the place to check out. Before I start, I just want to thank my friend Daniel Polencic, who's helped me put this together. I work with him in Learn K8. He's a bit of a legend. Well, so since you've come to this unexpected talk, I thought I should reward you, not just with knowledge, but perhaps with something else. I have one of these. It's a retro game that apparently you can plug into a computer and play 200 games on it. So this is up for grabs. Just because you come to this talk, I think I should give this to you. But the question is in front of you. Without Googling, can anybody tell when did this Oslo Spectrum open? Roughly. Have a guess. Have a crack. Whoever's closest gets this.
92.
92? Any other takers? Go for it. 95. Anything else? 80. Anything else? 88. 88 what? What are we saying 88 what? 88 which month?
August.
92 what month?
February.
Ooh. It's December 1990. So who's the closest? I think you are, right? Because you said August.
August 1988.
And you said, yeah, there you go. So you should not be disappointed that you came to this talk. You won this.
Oh, I'm happy.
Round of applause for our winner here. Yeah, we're getting somewhere. Awesome. So here's the agenda. I'll quickly explain what Kubernetes is and why perhaps it's useful. and I'll just, if you have any questions at any point, please do ask. This talk is specifically about how does Kubernetes place your workloads in the cluster. So Kubernetes has a cluster of machines that you can run your containerized workloads on, so we'll talk about that. And what you can do to move your workloads in a more efficient manner. So it's a little bit more advanced, but hopefully we'll all go through this together, and we'll cover a lot of stuff. If you have any questions, I'll put Q&A in here, but I prefer if you ask questions while we're going through it. So that's what we'll do. But you might start to think that, why is this important for me? I don't even use Kubernetes. If you don't use Kubernetes, hopefully there's some information for you to learn. But if you do use Kubernetes, OpenAI, people heard of OpenAI? OpenAI? It's like, yeah, it's an AI institution. They do a lot of work in the AI field. So they fixed the performance issues. They have a cluster with 2,500 nodes. So that's a pretty beefy cluster of machines, of anything, to be honest. And they have performance issues, and they fixed it by using Kubernetes scheduler and how to influence it. So, well, before we start, I know most of you in this room said you already use Kubernetes, but I think it's beneficial for everyone to give a 30-second recap on what containers are. So, sorry, I meant containers. What containers are? Containers, as you've seen, have, basically in the last few years, in the 5, 6, or 7, or the last 6, 7 years, we've seen a lot of uptake in containers. A lot of people are using containers to run their workloads on local machines, in dev, in production, wherever they might want to run their workloads. Predominantly because it gives you reproducibility. If I have a container that I can run on my laptop, I can take the same container that runs on my laptop, I can run it on a different machine. Operating system dependent, of course. And if there's any dependencies, I can include it in. But in order to run something, I need to have a runtime. In our case, I just put, because these slides are not for NDC, that's why there's a Java virtual machine. I would have put a .NET framework or .NET Core, whatever it was, if I knew I was going to give this slide. By the way, I wasn't supposed to give this presentation, but we're here, which is good. So imagine there's a runtime, any runtime. You could have Python, you could have JVM, you could have .NET, whatever it might be. And what you do is you take your artifacts, take all your files that you have, all your .NET files and all your artifacts, and you put it alongside this runtime, and you stick any external dependencies, so any packages that you want to install using NuGet, you put them all together, and you create this image which you can run over and over again. So this is what is now called a container. So JCE is Java Cryptographic Extension for Linux container. Windows container, Linux container. Outside, it doesn't make any difference. So outside the daemon, the Docker, or anything that runs it, outside it doesn't look any different. But when you peek inside it, it looks a bit different. But now we have a container. In the container, we have everything. So I can take a container, and I can create these containers using what's called a Docker file. If you already use container, you know. And it's just a set of instructions on how to build the application and run it. And once it's built, I can take that and run the container. I can do Docker run on my laptop. I can do Docker run in a production server. I can do it in the cloud, wherever I want to do it, everywhere it works. If I have one container, it's easy for me to manage. I can start, I can stop, I can delete, I can do whatever I want. Imagine your applications nowadays have microservices. And microservices, there's a lot of services that you have to look after. And you have a lot of services, then you have a lot of containers. And if there's a lot of containers, they will crash at some point. I don't know. If you're like me, perhaps you left a bug in the code and it will crash. And if it crashes, you have to start the container back up again. Managing one container is okay, but managing multiple containers is kind of hard. I mean, we wouldn't want to wake up at 3 a.m. in the morning and restart a container, right? Would you want to wake up at 3 a.m.? No. So why don't we let something else deal with restarting of the containers? And this is where the container schedulers, container orchestrators come in. Kubernetes being one of them, and there's other ones as well, HashiCorp Nomad and whatnot. And what Kubernetes allows us to do is basically automate this looking after of the container. So if it crashes, restart it. If I need to scale it up based on the traffic that's coming in. So I can define some metrics, and I say if the traffic isn't getting served within, 15 seconds from a container, scale out. And instead of running 2 containers, run 4, 5, 6, 7 containers, depending on what the traffic is. That's really good. And also, what Kubernetes allows you to do is run your resources quite well. As in, it will take a machine and it will try and fit as much application, as many containers as it can inside that machine. So, what is Kubernetes? Is everybody happy with that so far? Are we good? Right, excellent. That container can be an F# container as well. So if you're here for F#, this also applies, right? So that container can be an F# container. So imagine you have a cluster of machines. And in Kubernetes, what you do is when you have a cluster of machines, you make one in charge of everything else. And the one on the right, or to your right, is the Kubernetes. You can see the Kubernetes logos there. That's called the control plane. That's the thing that's the brains of Kubernetes. That controls everything. And the other nodes are just worker nodes. That's what the worker nodes are called. And we run containers in those nodes. And these nodes could be anything, to be honest. They could be a Linux machine. They could be a Windows server. They could be a Raspberry Pi. As long as it matches the requirement, the minimum requirement for Kubernetes, we can run anything inside it. And these machines don't have to be the same size. You can have a bigger machine or a smaller machine. So basically, I can create a cluster in which I can deploy the containers. Now, if you're running your application currently, and sometimes you probably have to deploy an application, container or non-container, whatever it might be. You might have to RDP onto a server. People RDP onto servers here? Like remote desktop connection, right? So you RDP, run the thing in, run the application, and then if you're doing a release, okay, where's the credentials? Try and figure out, let me just go and log into that server and deploy it. In Kubernetes, we don't do any of that stuff. We treat the whole thing as one virtual machine. Because right now you might have like 15 or 20 or 30, however many virtual machines you have. There's one specific server for database. There's one specific server for where you run your message queues. There's one specific server where you run your web apps. So there's a lot happening, and you have to kind of figure out, okay, in this box I deploy this, in that box I deploy that, and all that's happening. But in Kubernetes we say, nope, everything is just one virtual machine. So I'm just going to submit my container to Kubernetes. And I'll let Kubernetes decide where to place the container. So Kubernetes is playing Tetris. So I submit this request, and I'll show you what the request looks like in a second, because I think it might be beneficial using YAML files. So all I have is a container, and that container it's got nothing in it. It's just a simple web app, right? So .NET Core web app we're just running on there. And all I do is submit to the Kubernetes and say, Kubernetes, can you deploy this on your cluster? Kubernetes takes that request and it goes and it scans all the nodes to see which node are best fit. Now, which nodes are best fit is what this talk is about. How does it decide which nodes are best fit to deploy? Now, this comes in, it gets deployed, let's say, on let's call this one node 1, right? The one on the left is called node 1. Now, let me ask you a question. If we want to deploy another replica, because, we've got a lot of traffic, because we've done a release, people are excited to buy our products, so they'll come to our website, and then we say, actually, you know what, we should scale up. Kubernetes says, no, we need to scale up. We need to run replicas. We don't want to run the same thing. We run multiple replicas. If you were the Kubernetes scheduler, so that's the bit that decides where a container gets deployed, would you deploy this on node 1, or would you deploy this on node 2? What do you think? You can shout out. Node 1, who thinks node 1? Node 2. Oh yeah, so a lot of people think node 2, and nobody thinks node 1, which is excellent. So, there's a reason why Kubernetes does that, because if one of the nodes fails, and both of the replicas are on the same node, we lose both replicas. So it tries to see, okay, do I have enough resources? Can I deploy it? Should I spread it out? And that's what it does. It spreads it out and puts it in. And then another request comes in. This thing requires not enough memory, as much memory as CPU. By the way, the size of the box represents how much memory and CPU they require, right? All apps have different requirements. That's what the box represents. So the next request comes in. The next request comes in, and then Kubernetes looks around. Now, where would you deploy this? Node 1? Yeah? Node 2? Well, they're both similar. So, Kubernetes has to decide, and we'll see how it decides. And eventually deploys. Another one comes, again, we check, see what's going on, and it keeps deploying, and another one comes. It just basically keeps playing Tetris. The aim of Kubernetes Scheduler is to pack all the containers on every bit of resource as tightly as possible. Because what Kubernetes promises is that if you have your resources, as in your virtual machines or actual machines or servers, we don't want to waste any resource. I know there's a lot of research out there, and people say that typically, depending on where the research comes from, 70% of servers are idle most of the time. Would you agree with that? Some people are nodding their heads. Now, that's a bit of a waste of money, isn't it? Like 70% of the servers. So Kubernetes says, no, I'm not going to let you waste that money. Let's save some money. And it does that. Now, how do I submit this stuff to Kubernetes? What does it look like? What does the request actually look like? How do I tell Kubernetes, I want you to run this much replicas of this application, and this is the name of the container that I want you to run? How do we do that? Now, if you already use Kubernetes, you've come across this. But if you haven't, I'm going to show you a file. Let's just go in here. Sorry, this is very last minute, because this is a very last minute talk. Now, in Kubernetes, we use YAML files. People use YAML files here? Have everybody used YAML files? Yeah. Key value pairs. All we got is key value pairs. So you can see there's a lot of stuff, a lot of information in here. And there's a lot. And this is one of the reasons why Kubernetes is a bit complex, because you have to create all these files for your application to be deployed. We'll just ignore most of the stuff in here, and we'll just focus on the important bits. The kind of resource we want to create. And in our case, we say a kind is deployment. A deployment is a recipe of what your application looks like. How many replicas you want to run. So this kind could be a different kind. It could be a secret. So Kubernetes has some built-in kinds. And you can actually customize it to create your own kinds if you wanted to. You can create a SQL server. So if you submit that request to Kubernetes, it will create you a SQL server. But that's just an example. The other bit in here is replicas. How many replicas I want to run? I want to run 3 replicas. So if there's a lot of traffic, instead of sending it to one container, I've sent it to multiple containers. Now, this works well if the application is stateless. If the application has state in it, it's kind of hard to do, because where do you make sure the request goes in? So Kubernetes works well with stateless stuff. But that's a different topic altogether. These labels are just like information that other things in Kubernetes use to route the traffic. The important bit in here is this bit called the image. That's the image that you and I have built, the Docker container images that we built. And then this got some versioning in it. It says this is Nginx. Nginx is a web server. Think IIS, but very lightweight, like Linux-based container. And there's a version in it, 1.14.2 or whatever it is. And basically, this is how we take this file and we can submit this to Kubernetes using this command line tool called kubectl or kubecontrol, or some people call it kubectl. But you take this file and you submit that to Kubernetes cluster. Kubernetes cluster receives the request and he sees, oh, this is the container you want to run. These are the replicas you want to run. So that's, any questions on this? Is everybody happy with that so far? Cool. So let me just go back, if I can find my slides. Where do they go? Yeah, there they are. So this file that I showed you, we'll take that. You and I, let's say we'll pick one of us, right? One of us wrote that file and says we want to run this application. And what we say is we create this deployment file that I just showed you, and we say we want to run 2 replicas. Not one, we'll run 2 replicas, 3, whatever it might be. So we send this request to Kubernetes control plane, as I was showing you earlier on. Kubernetes receives that request, and the control plane is made up of different components. And all the components are here. So the request goes to what's called the API server. Again, it's a component in Kubernetes, runs inside a container. All the Kubernetes component also run inside a container in Kubernetes. So that's running in it's called the API server. So when you, from command line, you submit the request to the API server, it receives the request, and it takes that request, and it stores all the information that I showed you in the YAML file, the deployment, the replicas, and all that. In the bit on the right, that's a logo there. It's called the etcd. This bit here, it's called etcd. It's a database. It's a key value database. Think Redis. But it works very well in a distributed fashion. So you can run 3 or 4 of them or 5 of them. So if one crashes, it's called etcd. That's etcd, or some people call it etc.d. So that's the bit that stores all the information. Now, that is all the state of your Kubernetes cluster, as in what's running. what images are running, how many replicas do I have, what services do I have, what ingresses do I have, all this stuff. The idea being that if you take a backup of that etcd, which is just key value pairs, and for some reason your cluster gets deleted, but you have a backup of the etcd somewhere, you can go and restore from that and you get everything back. So the point is, the Kubernetes try to do is every time, all the time, is just reconciliating against what's written in etcd. So every time you change the state, Kubernetes says, I have to act on that change and make it happen. So anyway, so that's etcd on the right, and on the bottom you can see there's a component called controller manager, and there's another component called scheduler. So if you ever wanted to learn all the major components, there's more components, but just like main components in Kubernetes control plane, we have 4 main components in here. I'm talking about API server, this is control plane by the way, and etcd. As you can imagine, API server, all it does is it receives requests from everyone. And then we have a controller manager. Controller managers are the point for controller manager. And you can see now all these bits are also based on microservices way of thinking, right? So this controller manager does one and one thing only. There's different types of controller manager. But in our case, we'll say it looks at that request and says, oh, how many replicas do you want? Oh, 3 replicas. And it goes and creates those replicas in etcd. It actually writes them out one by one. Pod 1, pod 2, and pod 3. So imagine we want to deploy this bit called the scheduler. Oh, sorry, this application, this red page. It's got nothing in it. It's just an HTML page. It's just completely red. There's nothing specific, nothing special, just red page. But this could be anything. This could be your application, F#, C#, whatever it might be. Now, the controller manager is basically listening to the changes. So we submit the request goes to the API server stores that request in etcd. And controller manager is listening to etcd all the time. And it says, oh, right, there is a deployment for me with 2 pods in it. Pod, by the way, is, I should explain, you and I talk about containers. Kubernetes does an abstraction. It says, I'm not going to talk about containers, I'm going to talk about pod. And pod could be just one container or collection of containers. So in a pod, you can run multiple containers, or you can run one container if you like. Most of the times you run one container, but there are some use cases when you want to run multiple containers. How are we doing, by the way? Is everybody okay? Yeah? Are we good? Cool. Nobody missing F#, I hope? Yeah? Excellent. Let's carry on. So the request comes in. The controller manager goes, okay, I know what I need to do. I will create you these two pods. I will create those pods for you. But actually it doesn't create the pods. It just writes the information in etcd. It just says, okay, I'm going to write this information in etcd, because etcd is where we said is where all the information about the state of our cluster is. And then what happens is, once you can see, we say there's 2 pods, pod 1 and pod 2, and they have a status. They could be running, they could be pending, they could be whatever. And as soon as the status changes to pending, there's the other component called the scheduler, is listening in for that specific change, for that specific status. And it goes, oh, there's a pod that's gone pending. It's my job now to figure out where these pods have to be run on the cluster. So the scheduler then goes around and scans the cluster and says, okay, I'll deploy this in this pod or that pod, or we'll try and schedule it. Now, so what we'll do is we'll focus on what the scheduler does. Just information. By the way, I stuck my Twitter handle in, Salman Iqbal. If you have any questions, best way to find me is there. Or the comment section in YouTube. You can message there. So there's 2 phases the scheduler does. Scheduler's got 2 things. It's got the scheduling phase and a binding phase. We're going in a bit of detail, but hopefully it's going to be useful for you. And we'll play a game as well in a little while. There's a game that comes up we can all play together. So there's in the scheduling phase, the scheduler decides the best node for the pod. And the binding phase, that's where it says, I'm going to assign that pod to the node. Pod is a container or a collection of containers. That's what a pod is. Now, as soon as the pod is created by the controller manager, so the first component that we talked about before, it also is added to the scheduler's queue. So everything gets added into a queue, kind of like how we have this queuing stuff. So pod gets added to the scheduler queue, so it picks up the first one and starts doing what it needs to do. And then to decide if a worker node, so I could have 2, I could have 5, I could have 2,500, like the Open API people did. To decide if a node is suitable for a pod, the scheduler scans and filters the nodes. Now that's important in a second, and I'll explain. But filtering sometimes is not enough. In most times, filtering is not enough because you could end up with multiple nodes, multiple worker nodes where you can deploy this pod. So how do you decide? And this is where the scoring comes in. So each node then gets given a score. And we'll look at what scoring is. And after scoring is basically the notifier and the binding policies. The deal is basically done by that after that time. So scoring, once the scoring is done, you just need to notify some components to say, okay, this is where it's going, and then basically we bind the container to bind the pod to that node. And then this is where the binding happens. Binding is yet another object. All that says, if you look at it, says pod 1 runs on node worker 1 or worker 2, whatever it might be. That's all that does. Again, just like everything else, information about your application, about the state of your cluster, is all stored in this. Where do you think it's all stored? Let me ask you a question. In the etcd database, right? So etcd database is the bit that stores all the information. So every information about your, not the application information, because that belongs to your application, about the infrastructure, where your containers are running, what are they listening to, that gets stored in etcd database. So now what we've done is we have scheduled the pod. We've scheduled the pod and we said, okay, this pod is going to run on worker node 1 or worker node 2. But so far, nothing has actually been created. We actually haven't run the pod. The pod is not running yet. We've just updated etcd cluster. So all we've done is taken etcd to say, okay, there was a pod that was pending, but now it's scheduled because we figure out, we update this information and say, okay, pod 1, you're going to worker 1. Pod 2, you're going to worker 2. So who actually creates the pod? Well, I said we don't really log in and start or stop the containers. So every time there's a cluster, in the cluster, you have the control plane in which all the other components were. And then we have the worker nodes. And in worker nodes, there's a component called kubelet. Again, it's just a process. It's a binary. It's just a bunch of code that runs in a container on every worker node. And all the task for kubelet is to speak to the control plane and say, is there any pod for me to be run on this worker node? That's all it asks. So all it's asking is there any pods for me to run? So if there's 3, if one of them gets deployed, if one of the pod is assigned to worker 1, basically it will take that request and kubelet will call a container runtime. A container runtime could be anything. Could be Docker, could be containerd. But right now, let's say it's Docker. And all Docker container runtime, in our case, is Docker. And all Docker, it's a Docker daemon. And all it does what we do with the containers. Docker run. It just runs the container. All it's doing is running the container. So now the container is up and running. It's all good. But let's take an example. Why is this important, right? What am I talking about? Imagine we create a deployment, right? A deployment file that I showed you before. Information in a deployment file is how many replicas I want to run and what container am I running, and some extra information that we need to fill in. So we write that YAML file. In our case, we give it some requirements. We say, okay, I need to run 1 replicas, and I want it to use a GPU. GPU, we run like machine learning stuff, or your gaming stuff runs on GPUs. I don't want to deploy it on CPU. I want to deploy it on a GPU, and this is the memory and the CPU requirement for the container that needs to be run. And this is our cluster. I've got 12 worker nodes, right? I've got 12 worker nodes. Some nodes are already full. So you can see the ones with yellow, and if you see in the top row, the green one is half full. The yellow one is half full. The bottom ones, there's like pretty much full. There's 2 full. Most of them are CPUs, but there are some which are GPUs. You can see that it says they're GPUs. So they support GPUs. And our requirement is to run it on a GPU. So the first phase of the scheduler, as I said in the beginning, is filtering. It filter out the nodes. And I'm sure we can all agree the requirement is to run it on a GPU, so we get rid of the CPUs. Scheduler goes, yeah, you're out. You are not of no use. So it takes the CPUs out. And then we got 4 GPUs, right? And then what it says, hopefully when you got 4 left, which one should you pick? The scheduler then ranks and prioritizes the nodes. And there's an empty one, right? So you can see at the bottom there's an empty one. Why don't we pick that? Because it's empty, let's just deploy it on there. But it's got this ranking there, 1, 2, 3, 4. You might see 3 and 4, they're quite similar. It's got two pods running in there. How did it rank one with number 3 and one with number 4? That's kind of, what did it do? How did it do that? And we'll just look at all of this now in a few seconds. So what it does is then it basically takes that and runs that pod on that node. And everything's good. People can send requests to this pod. Well, it's running on a GPU or whatever it is. And everything gets, traffic gets served. Everything's good. Any questions so far? Is everybody okay? Yeah? We're good? Cool. I know it's the last, we're getting to the end of the day, but it's the first day, so, it's, hopefully we're all good. Now, filtering. We said filtering happens. So how do we do the filtering? Well, filtering happens in lots of stages. Well, Kubernetes has these things that it goes through, what it calls predicates. Some checks that it does. It does a lot of checks, right? So it's doing some checks. And it has quite a few checks, 12 of them. I'm not going to go in detail, but let's say if it's a web server. A web server needs to be run on a server. If it needs to be run on a server, we've all done this. Hopefully, if you run on a server or whatever, we need to make sure the port that it runs on is empty on the virtual machine, right? We've done that. We just make sure the port is free. Otherwise, it's running on a different port, right? It's a web server running a different port. And that's kind of what Kubernetes does. It checks, if I deploy this container on this node, does it have that port free, the one that's required by this web server? If it doesn't give it it just says, yeah, you don't have a port free, so I can kick you out. But if it does, it picks that. And then basically, sometimes you can say a pod needs to be deployed on a specific host. You can say like a specific machine with this name. If you wanted to, you can do that. And there's tons more, right? So I'm not going to go through all of them. There's like memory pressure just checks to see if there's enough space on if there's enough space on the node. There's some tolerations. We'll talk about tolerations, and also looks at like, can I bind any volumes? Sometimes the pods might need information from a disk or something. So if you can apply that. But the point is, it's not important to know each one of them or what they are, but it's just Kubernetes does all these checks to see if it can fit the pod on that node. But it's not done yet. We've just done the filtering. There's a lot of checks, but we have one more stage to go, which is called the scoring stage. And it's basically similar. When it needs to score, so we did the filtering, and now we're going to do the scoring. Again, it does the similar thing. So it's got a list of 12 things it goes through, and basically spreads across the hosts. Same thing again. I'm not going to go through them all. Just make sure that the pods are spread across all the nodes, because we don't want to deploy them on the same node if there's replicas, or because if we lose that one machine, we lose all our applications. We don't want that. That's not good. And Affinity stuff, but again, there's tons of checks it goes through, and it starts giving them a score. Now, the scheduler actually is optimized to make the best placements about your application. That's what it's optimized for, right? And that's the promise. The Kubernetes will say, okay, you send me the request, and I'll figure out where it needs to run. So you don't have to worry about this. But sometimes you might know your application better than Kubernetes does. And we look at some of the use cases. That way, there's 4 mechanisms in Kubernetes that help you influence the behavior of the scheduler. Because the scheduler is doing his thing. We saw those 2, filtering and scoring. But we can say basically influence the scheduler's behavior. And there's 4 checks four hints we can use. One's called the node selector. Hopefully that kind of makes sense. You can select a node. There's something called the node affinity, and pod affinity, anti-affinity, taints and tolerations. These terms might be new, but we'll break them down and explain them. So if anybody asks you, and when you go back to your office, to your Teams, when you Zoom call, how do I deploy this pod? You can tell them all about it. So node selector is the simplest one. And I actually have used it quite a lot of times, because there's some cases where you might want to use it. What nodes have is labels, and labels are just key value pairs, random key value pairs. You can say server is the key, and the value is web. Just random key value pairs. You can attach them to the nodes. You can go kubectl. Well, I'll show you the command in a second. And pods, the labels I was showing you in the beginning in the YAML file, they have what are called selectors. Again, they're also labels. So what you can do is you can get these selectors to target the nodes. That's what it is. When you write you say, oh, just select this node selector. You write in the pod YAML, you say node selector, target the labels. So let's take an example. Imagine I have 4 nodes here, and we can deploy the apps on them. And what I do is I assign a label. I say kubectl label nodes, and I say worker 1, which is kubectl is a command line tool. Worker 1 is the node, and then app equals red is the label. I just attach that label. It's just simple label, nothing special. I just attach the label to it. In this case, we assign the label app equals red to the first and the third node in the cluster. You can see the first one and the third one, right? I just say worker 1 and worker 3. And here's my deployment file. We saw this before, right? A deployment file came in late, but we can quickly look at it. Deployment file, it says I need to run the 3 replicas, and halfway through, and then at the end there's this thing, the image that I'm running, and the node selector. The box should be a little bit lower than that line, but you can see node selector is app equals red. So we're saying this pod needs to be deployed on the label where on the node which has the label app equals red. Now, there's 3 replicas. Let me ask you all a question. Where do you think the pods will get deployed? Let's start from the left. 1, 2, 3, and 4. Where do you think they will get deployed? Just shout out. It's okay. There's no 1 and 3. Very good. Very good. We have a first answer. Excellent stuff. There's a few more, so feel free to shout out the answers. So 1 and 3. We can deploy to 1 and 3, right? And there's space for two containers. We just deploy them on there. On the first one, there's not enough space left, so we go and deploy it on the third one. Hopefully that's clear. So this thing has to have an exact match. If the labels don't match, no good. It's a hard requirement. So if there's not enough space, your pod will not run. So consider you have this existing cluster, and I scale the replicas from 3 to 5, right? 3 to 5, I go from 3 to 5, and the node selector is red. So it went from 3 to 5. Where do you think the pod will run? Any guesses? We got 5 replicas. Any guesses? Go on. Yeah, one is already full. Do you agree? 1 is full. What about 3? Can we deploy a pod on 3? Yeah, we can deploy 1 pod on 3, and the other one just stays pending because there's a hard requirement. And you'll say, oh, that's terrible because I have 2 worker nodes which are completely empty. Agreed? They're completely empty. Why don't we use that? And that's why Kubernetes says, okay, if you want a bit more flexibility, you can use node affinity. So we're building up now. So we're building up a little bit more. Now I'm going to flash this next slide, and it's going to be a big label on there. But let's ignore the label, because whatever it says, required during scheduling, ignored during execution, I don't even know what that means. That means hard or soft requirement, right? So there's 2 things. That's how I remember them. I don't remember it that way because that's too long. So hard or soft requirement. So you can, with node affinity, have a hard requirement or a soft requirement. For example, hard requirement will be only run the pods on nodes which have GPUs. That makes sense, because if a pod requires GPUs, you can't really run it on CPU. It'll take a lot longer. Well, it won't even run. A soft one is something like this. Run pods in, let's say, UK first. You have a node that runs in UK. Run it there. Otherwise, run it somewhere else. So otherwise, run it somewhere else. That's what that is. It's hard and soft requirement. So again, we'll do another example, and in the same cluster, I attach the labels. We've got 2 labels, and it looks a little bit weird. Sorry, we're going into a lot of YAML files here, but this is basically required during scheduling, ignored during execution. This is a hard requirement, and you can see the key is app, and operator is in, and the values is red. All it says is if it has app equals red, that's what our affinity is. So that's where we wanted to run the container on. And now this is very similar to what we saw before, because it's a hard requirement, which is exactly the same scenario that we saw previously. And I can take them and, like it will basically go in. I've got 3 replicas running. If I scale up to 5, basically the same thing will happen, right? Everything will be the same. Another pod will run there, and one will stay pending. So nothing is actually changed. Nothing is actually changed. But I can do this node affinity with prefer during scheduling and ignore during execution. Sorry, the highlight is a little bit higher than it should be. I'm not sure why, but it's there. But it should be on that long label there. So this is a soft requirement. What do you think will happen to the pods now? It's a soft requirement. It might end up on pod node 2, node 3, node 4. Do you agree? It might end up on it. Yeah, that's exactly what happens. But if it's scheduled, you kind of have to delete it. But the point is, if you use the soft requirement, you can basically go ahead and you'll say, okay, there's no nodes left. I'm gonna deploy it on there. I know this is boring stuff, but some people have this issue. They might figure this out. So there's another thing. Sometimes you want some pods to run together or not. You might not want to run them together. And if you want to run them together, for example, you have a trading app. I don't know, something that requires microservices. We've got microservices. Imagine you've got all these nodes. Some nodes are deployed in Finland. Some nodes are deployed in Norway. Some nodes are deployed in USA. And the pods could be deployed anywhere, right? They could be deployed anywhere, any of the nodes. If that happens, how do we reduce the latency between the traffic that goes between all these containers? And this is where we use pod affinity and anti-affinity. You can get pods to stick together or repel. That's basically what this is. Stick together or repel. And affinity and anti-affinity is based on labels. So we got labels specific for namespaces, but that's basically we just keep using the same labels as before. Now imagine I have this pod with app equals red. So app equals red is the pod, and I'm going to show you another file here. We got labels app equals red with the label that we attached, and we deploy all the red apps like we would, and everything gets deployed correctly. And what we want to do is we want to deploy this green app, right? And this is with a different label and pod affinity, and we define basically pod affinity in this pod definition. We just take the pod definition again. We define that. And here you can see this pod definition, and we say, okay, this pod has to be run next to the pods, which has app equals red label. Right? That's what we're saying. So this green application needs to run with the pod, which has that red label. So I'm sure you're all thinking, it gets deployed here. So again, we can get these pods to talk to each other, deploy them close to one another, and that's what happens there. And it's the same thing. I've got this yellow one, and in this yellow one, I just tell it run it next to the red pod, and this yellow one goes in, and it goes again the same kind of thing you can imagine. It will get deployed to the red pod when there is, if there's a requirement for it. Right? I'm just going to skip that. Now, just like node affinity, pod affinity and anti-affinity can also be hard and soft requirements. That's just the way Kubernetes scheduling is done. And you can decide to change the scheduling and say, okay, I'm going to put a hard requirement or I'm going to put a soft requirement. And if there's this, just like before, if there's no space next to it, it'll go and deploy somewhere else. But if there is space next to the container, it'll run next to it if there's a soft requirement. If it's a hard requirement, it'll just repel away and not deploy there. So that's what this is saying. Same kind of concept. We won't play the game, but I'm sure you understand. We'll basically go ahead and get run and get deployed there. And anti-affinity works in the opposite way. All we tell it is to repel any of the labels that we want it to repel. We want it to repel app equals red or app equals green. And so this is the yellow app, and we tell it to basically repel it. In this case, we said app equals red and green. We don't have anything with red and green label, so it just goes ahead and deploys on the last node. There's some constraints where if you use anti-affinity, you're doing a lot of calculations. It's trying to figure out, oh, can I run here? Can I run there? It takes a lot of time, so it could eat up your CPU and memory. And you can basically, it's useful when you want to schedule the pods together. And sometimes when you don't want to run the pods together, maybe it's for some compliance sake, so you can basically repel them using this anti-affinity. Now, this last bit is the most confusing bit, but I'm going to try and do it in the least possible, the least confusing way. Hopefully, it's just the way the API is written is a little bit weird. But I'm getting recorded, but I don't mind saying that because it's kind of hard to understand. But once you get it, it makes sense. But in this case, what you can do is you can get nodes to repel the pods. That's all we're saying. Sometimes you can say a node, if you need to upgrade a node, let's say you're upgrading a node, but you want zero downtime, and you don't want anybody to deploy anything on there, so you can apply these labels, apply these taints to repel all the pods. So nobody can schedule a node, nobody can schedule a pod. Once everything's set up, you can start deploying it. It's basically the same as node selector, but the label is slightly different now. Instead of adding a label, you add a label with an effect. You say this is the label and this is the effect. And when you do that, and there's 3 effects you can have. No schedule, prefer no schedule, and no execute, which is basically hard, soft, and evict. Kind of like what we had before. Pretty much the same, apart from we added one more behavior, which is evict. So if the hard and soft don't match up, just evict the pod. If it's running in there, just, if it doesn't tolerate that, evict the pod. That's what it does. So this is perhaps the most confusing bit, and we'll be done. We don't have much long to go. And what you do is you taint the nodes. So you have all the nodes. What I'm doing is tainting the node using this command called kubectl taint nodes, and app equals yellow no schedule. And what the no schedule is the evict taint. Now I'm gonna do the first one, and hopefully you'll see it. So we have cluster with 2 taints. You can see app equals yellow, no schedule, and app equals green, prefer no schedule. Prefer is the soft one, and no schedule is the hard requirement, right? So prefer is the soft and the hard requirement. You can see we get this hard and soft in different use cases. We decide to create a deployment of a red pod, and what we do is we create a deployment with a toleration of app equals red. Right? We just say it can tolerate app equals red. And the thing with the labels, which is the weird bit, is if you tolerate that label, the pod tolerates that label that's there, which is app equals yellow, app equals green, then the effect that's there doesn't apply to that pod. It's a bit weird. It's just the way the API is. If it doesn't make sense, don't worry. It's just the way it is. But in our case, we don't actually have app equals yellow, app equals red label here. There's one node which doesn't have any labels. It will go ahead basically and deploy it there. And if we increase it to 3 replicas, it'll basically deploy one in the last one, which is empty. And then if you see the one in the middle that says app equals green, prefer no schedule. So it only actually prefers, the middle one, only prefers to deploy pods which have app equals green node. It prefers. If it doesn't have app equals green label, it will deploy it if there's no other space for it to go. The one on the left will only deploy the pods which have app equals yellow label. That's just the way their API is written. It's a bit weird, but kind of works in those use cases. So in our case, we scale it from 3 to 5. The middle one gets another pod, and there's one stays pending. So that's what it is. And what you can do is, if let's say you want to upgrade your worker, because with zero downtime, you can add app equals green, no execute, which is worker 3, and all it will do is it will evict all the pods. Does that make sense? If it doesn't, blame the Kubernetes people who wrote Kubernetes. But if you have any questions afterwards, you can ask us. Again, same thing with this. That's what this is. So, why is this? When is it useful? All the containers are usually scheduled on worker nodes. The worker nodes the nodes that we deploy, the pods that we deploy, they don't get scheduled on master node, or on the control plane. So this is where on the control plane, when you check, it has this taint which says no schedule for everything. So nothing. It just says control plane, key control plane, node control plane, no schedule. So it doesn't deploy that. So let me just finish up. We've got a couple more. We've got 5 more minutes. So if node selector, node affinity, pod affinity, taint and toleration aren't enough, you can influence the scheduler by writing your own plugin. Again, the bits that I showed you in here in the beginning, you remember this diagram. The filtering is basically there's more stages to it rather than the simplified version that I showed you. And scoring as well, you can see there's more stages to it. Just every bit does its own thing. And the blocks at the bottom, and all the bits that you see in the top, you can modify them. You can write your own custom logic to it. The bit at the bottom, the binding, you can't really change that. That's what it is. And if you want to customize any of the plugins, you can write your own logic. And if you look in the middle one, this QSort plugin, all it does is just picks one pod and returns it. You can write your own plugins for it. And if none of the options work for you, you can actually write your own scheduler. So you can say, forget about the Kubernetes scheduler. I know the logic better. You can actually write it as a pod, like your own logic. You have to read your information from etcd, and you can write that. And I know I'm bombarding you with YAML files, but unfortunately, Kubernetes is all about YAML files. And then you can tell a pod to use a specific scheduler that you wrote. So you can do that. So Kubernetes, if any pod has that scheduler, it ignores everything by default. It ignores the default scheduler. And you just have to kind of watch everything from an API and write your own logic. And this is the pseudocode, an example of that's written here. All it does is it gets all the pods that are there that needs to be deployed, and it basically picks a node at random. You can see we just do a bit of random logic here, and we then assign the pod to the node, and this is what the assignment looks like. Again, it doesn't really matter too much what it looks like, but all we've done now is basically deployed our container there. Now, you might say, what are the use cases, right? So this is the last bit. What are the use cases? Why are you talking, instead of talking about F#, why are you talking about this crap? Well, this is why it's useful. So there's quite a few use cases. Imagine you have a GPU, and you have a load that you want to run on GPU, so I can use a node selector and node affinity. That's the kind of thing I can use, right? So that's a good use case. And I can use taints and tolerations, where the node control what actually gets deployed on that pod, on that node itself. So maybe you want to upgrade a node with zero downtime. You can basically taint that node so nothing gets deployed. Or we use control plane. We deploy like with taints and toleration. There should be an S there, but there's a Y. There's a bit of a mistake there. And you can use pod affinity to group pods together, and if you want to reduce latency between two pods, so let's say you have an application you want to reduce latency, you can use pod affinity, anti-affinity, or as OpenAI, I talked about that in the beginning, found out you make sure that not all pods get deployed on the same node, because that's what they came across. So OpenAI found out this issue where they had a node with 2,500. They had a cluster with 2,500 nodes, and there's a service in Kubernetes. Again, it runs as a pod. Basically, it tries to figure out where all the pods are running. So if a pod wants to talk to another pod, if a container wants to talk from one container to another container, this is a service called kubedns that figures out, oh, this pod is in this node, that pod is in that node, but that one crashed, so now it's somewhere here. So that service is very, very important for Kubernetes to work. Otherwise, it doesn't work. What they found was that they found that on some nodes there were more than 10 instances of kubedns running on more than 10 instances, and this was actually running in Azure. And in 2018, each virtual machine in Azure had a query per second request of 200. So you can only request in the virtual machine, you can only request like 200 queries per second. But because we had 10 instances of kubedns running on each node, more than 10 instances, and they're constantly talking to the API, way more than 200 requests per second. And what happened was everything was getting throttled. So none of the stuff was getting deployed. So they looked at it and go, oh crap, that's what's happening. Then they used pod anti-affinity to make sure that pod repelled themselves. So instead of basically they had 2,500 nodes, they used pod anti-affinity to repel all the pods and just run them on all the nodes instead of like more than 10 running on one node. So that's what they did. Now, any questions? No? Okay. So last bit, the recap.
Yeah,
Sorry, go for it. kubedns, yeah.
Is that like Dapper or not?
Is that like Dapper?
Yeah.
No, it's basically it's not Dapper. It's just a logic that kubedns logic. All it does is updates IP tables in in the machine. It's not like Dapper. It's literally all it's doing is just updating IP tables. It says, oh, this pod has this IP address, that pod has that IP address. All that's doing. But that's a good question. But it's just is logic that runs in the cluster, kubedns.
I also have a question.
Sure.
You mentioned earlier when the port selection, you could do filtering on ports.
Yeah.
So you could have two of the same port for the same node.
Yeah.
But assuming, I don't know how kubedns works. Does it do like routing kind of thing? And then it's like, why wouldn't it just put it on a different port and then route it to that port on that node?
Yeah.
Or is it just a pure DNS?
No, that's it. So the question is that I said one of the things that Kubernetes checks in the beginning is the port free, right? That's the question. And then your question is, which is quite good. It says, why can't kubedns be a bit more clever? And it says, oh, that port doesn't exist, so maybe I'll change the port to this port and deploy it. Is that right? Yeah. So the reason why it doesn't change the port is because that port definition that we write in deployment is written by you and I. So that's why Kubernetes doesn't change that. Because otherwise you have to like track one more thing to change it and then route it. So basically, the YAML file that we wrote, that has the port. Does that make sense? Does that answer your question?
Kind of.
Okay. Basically, it doesn't do anything fancy with the port. It just takes that information and says, yeah, that's the port running on. I'm just going to deploy with that port. It doesn't try to do anything fancy. Because that's not the Kubernetes, that's not its main job. That's not its main job to like figure out. All it does is just basically updates where the pods are, what its IP address is. That's the Kubernetes' main job. But perhaps you can write a component to do that, maybe like update it or figure out. But that's a very good question. Any other questions? Okay. Last slide. The scheduler is in charge of deciding where the pod is deployed in the cluster. And the scheduler goes through two phases, scheduling and binding phase. And there's like a lot of filters and predicates that we talked about. And then there's the simplest one, node selector. You can select a node to run, or you can do node affinity. So you can figure out if a pod can be placed on a particular node, and you can do pod affinity and anti-affinity. You can repel them together. You can repel away if you wanted to. And Taints and Tolerations get nodes to repel the pods. You can update your logic if you wanted to, and you can write your custom scheduler. But if you want more information on this stuff, you can always message me on Twitter. I'm still around. You can catch me. You can go to the websites. We've got learncase.io. We've got some really sick blogs on there. At via.io, we've got some really good blogs as well. You can go to Kubernetes documentation. If you have any questions, you can find me on Twitter at Salman Iqbal. I also have a YouTube channel. But I'd like to thanks all of you for turning up to this unexpected session. I hope you found it of any use. I've been told that after 5 p.m., the only card you can use is green. Is that right? Is that right? So when you... No, I'm joking. Feel free to give an honest feedback. But any questions? Are we good? Okay. So thank you all for joining. I really appreciate it. Hopefully you found it useful. Thank you.